Hello, today we're going to do an unusual integral from the 2022 MIT Integration Bee. So it's quite unusual because of this fractional part function, which basically only keeps the fractional part of a number. So in this case, 2.5 would just be 0.5, and we ignore the integer part of this number, and so on and so forth. For 4 over 3, that just gives us 0.333 or 1 over 3. Pi would give us only the decimal digits of pi. And then a second function that we need to look at quickly for this solve is the floor function, which gives the number rounded down to the nearest integer. So for example, 1.9 would be 1, pi would be 3, and so on and so forth. Not too difficult, but they are quite difficult to work with, or tricky at least. So let's see how we do this. Let's first maybe notice something before we get started, and that is that the fractional part function of x could be decomposed into x minus the floor function. So I hope that makes sense. We take the entire number x and we subtract the integer part, the floor of x, and we get our decimal fractions, fractional part at the end of that. So we're going to use that to solve this. And second thing we're going to do is we're going to consider a more general integral, just so that we don't have to work with these massive numbers. So the integral from 1 to a of the fractional part of x over x dx. Now we can write this integral as the integral from 1 to a of x minus the floor function of x all over x dx. And notice that we can split this up into two integrals. One integral from 1 to a of x over x, which is 1, so that's just going to be dx, and then a second integral, so that's going to be minus the integral from 1 to a of the floor function of x over x dx. And it's mostly this second integral here that we'll have to deal with for the rest of this video, because this first integral is just a trivial integration, which is going to give us, let's see, a minus 1 and then minus our other integral. Now we still have to deal with this monster here. So maybe notice that this over x part isn't actually too difficult, where you can integrate that, but this floor function part is quite annoying. Let's see how this floor function behaves, and let's notice maybe that we can split this up into different parts. So let's get this integral from 1 to a of the floor function of x over x dx. So we'll consider the following integral, and let's see how this integral behaves over several different intervals. So let's say we split this integral up in the integral from 1 to 2 of the floor function of x over x dx plus the integral from 2 to 3 of the floor function of x over x dx plus dot dot dot, and then let's say from a minus 1 up to a of the floor function of x over x dx. So why have we done that? We can now actually look at this floor function and simplify it a lot. So let's look at the interval from 1 to 2 for x. So, well, the floor function on that interval is actually just going to be 1 all the time. I hope that's logical to you. Any x between 1 and 2, let's say 1.5, for example, the floor function of that will be 1. 2 itself wouldn't be the case, but it doesn't really matter for an integral, so we're going to ignore that. So let's just get rid of this. We can write in 1 dx. Now on this next interval, we can do a similar thing. We're going to get, well, 2. On this interval, we're always going to get 2 for our floor function. And then the next part, well, we're going to get a minus 1. So on each of these intervals, we can simplify our floor function because it has been contained on that specific interval. So in the end, we can get this sum, and let's now use summation notation from, let's say, n equals 1 up to a minus 1 of the integral from n up to n plus 1 of n over x dx. Awesome. So let's bring this result over here. So we've got a minus 1 minus the sum from n equals 1 up to a minus 1 times n times the integral from n to n plus 1 of 1 over x dx. So this next part is going to be equal to a minus 1 minus the sum from n equals 1 up to a minus 1 times n, and then times the logarithm of x evaluated from n to n plus 1. So again, this integral is quite trivial. I guess if you haven't seen that one before, just look it up. It's well known that the derivative of log of x is 1 over x. Now we can write a minus 1 minus the sum from n equals 1 to a minus 1 times n times the log of n plus 1 minus the log of n. But we can also maybe use logarithm rules to just combine these in one log. So let's see, we're going to get the log of n plus 1 over n because of the minus sign. And now we can also combine this even further. So we're going to get a minus 1 minus the sum from n equals 1 up to a minus 1 of the log of n plus 1 to the nth divided by n to the nth. Let's see how we can simplify this even further. It's quite an involved process, but we're going to do it anyways. So first of all, we've got logarithms, and we've used some log rules already. We've got that constant in front as an exponent already, but also if we add logs, so let's say log of, let's say b plus log of c, that's going to equal log b times c. So notice that we've got this sum. So actually we can make this sum into the log over product, right? So let's see how we do that. So we're going to get a minus 1 minus the log of the product from n equals 1 up to a minus 1, and then of n plus 1 to the power of n divided by n to the power of n. So this product denotes the exact same as a sum, but then we're going to multiply each term. So let's give some examples here. So we're going to get, let's see, 2 to the power of 1 for a first term n equals 1, divided by 1 times, let's see, 3 to the power of 2 divided by 2 to the power of 2 to the a minus first divided by a minus 1 to the a minus first power. And now we can actually see some massive simplification, which is really quite nice in this product here. So what are we going to see? We're going to see that this 2 and the exponent here cancel out. So basically we've got 2 times 2, and we divide by 2 times 2, and we multiply by 2. So this is just going to be 1, and this exponent is going to go away. We're going to see that pattern repeat. So this 3 to the second divided by 3 to the third makes this all go away into a 1 and erase this exponent. So one more time, let's see, we're going to get 4 to the third divided by 4 to the fourth. So we're going to get 1 divided by 4. And on the denominator, we can now see a factorial forming there. And this process is going to continue. So this is going to be 1. And this exponent is going to be erased. Now we can say that that this equals a minus 1 minus the log of a to the power of a minus 1 divided by a minus 1 factorial. And thus our integral from 1 to 2022 of the fractional part of x divided by x dx is going to equal 2021 minus the natural logarithm of 2022 to the power of 2021, all divided by 2021 factorial. So awesome, we found the solution we needed. So maybe one more note before we finish. A actually does need to be an integer, otherwise we need to consider one more part of this integral, which isn't too difficult, but I thought it brought us too far and it didn't really help us for our case of this integral, a being 2022. Now we could actually rewrite this slightly, again using logarithm rules and getting for some people an even nicer result, but I think this result is also quite cool. So thank you so much for watching. I hope you enjoyed this result. Pretty complicated integral, and I hope you learned something about floor functions and fractional part functions. Thank you so much for watching. Also, let me know if you like the generalization more, or if you wanted me to keep just this particular integral. Till next time, thank you so much for watching.